Hello, welcome back. In this segment, I wanted to talk about when you multiply two numbers, how do we check whether the answer is actually safe, meaning the answer is trustable? Okay, that happens because if you multiply two numbers, the answer may not fit in the resulting memory size, right? For example, let's say A is a 21-bit number and B is, for example, say 2 power 12, right? So this is your A and this is your B. So if you multiply 2 power 20 into 2 power 12, you would get 2 power 32. But 2 power 32 requires 33 bits. Okay, so it doesn't fit in the memory model of unsigned integer. So what shall we do in that case? In that case, when you multiply 2 power 20 into 2 power 12, 2 power 32 mod 2 power 32 will be computed. Okay, in many implementations, this is how overflow is handled. So 2 power 32 mod 2 power 32 will be 0. Okay. That means multiplication is not correct here, right? You send a 2 power 20, you put into 2 power 12, you get 0 as the answer. So you can't trust the answer because it's mod 2 power 32 is happening under the hood. Okay. But how do we check whether our answer is safe? That is my question that I'm investigating in this segment. Okay, let's go through the program that I wrote here to check whether multiplication can be done safely or not. The program takes two inputs A and B, right? Unsigned integers. And what it does is before multiplying, it extends the type of A to a 64-bit number, okay? Which is possible because in the C language, there is something called unsigned long. So I created a new data type called unsigned underscore 64 to represent unsigned long. Okay. Why is 64 enough? If this is a 32-bit number, this is a 32-bit number. If you multiply two 32-bit numbers, right, the maximum value will be 64-bit number. Okay. You can simply take, say, a two-digit number. Let's say A is 11 in binary, right? And B is 11 in binary. If you multiply A and B, you will get an answer which is in 4 bits. For example, A times B will be 9, right? If this is 3 into 3, 9. 9 requires 4 bits, right? This is 9 in binary. Okay, so when you multiply two 32-bit numbers, you may get at most 64-bit number. So what I'm doing first is I take A and cast it into a 64-bit number. Okay, so the resulting product will be a 64-bit number here. All right, and I'm also doing multiplication without the conversion from a 64-bit, without doing a conversion to a 64-bit, and I'm checking whether these two are equal. Okay, if they're equal, we can say they're safe because there's no change. Even if I make the number A pretend like a 64-bit number, right, and multiply it with B, and there is no overflow, therefore they will be equal. Okay, that is the algorithm essentially to check whether two numbers can be multiplied safely without any overflow. Okay, and let's do some test cases to convince ourselves that this is reasonably okay. Testing doesn't show you absence of errors, but we can play with different examples to get an understanding. Okay, all right, so let's take A and B to be 0, initialized to be 0, of course, and take A to be 2 power 20, B to be 2 power 11. This is 2 power 20, this is 2 power 11. And we can be sure when you multiply 2 power 20 by 2 power 11, you get 2 power 31. And 2 power 31 perfectly fits in our integer representation size, right? This will be, what will be the value of C for the first test case? 2 power 31, right? And D will also be 2 power 31, and they are equal, so we are good. So good in the sense, answer will be 1. Okay. And the next test case, right? Next test is interesting. I put A to be 2 port 20, B to be 2 port 12. So it'll be 2 port 32, right? 2 port 32. If the implementation uses modular arithmetic, right? What will happen in that case? Our C will be 2 port 32, but our D will be 0 because 2 port 32 mod 2 port 32 is 0. So C and D are clearly not equal. Therefore, we get 0 from here. So this will be 0. That's the reason why assertion is compared with 0. Okay. Okay. So let's put breakpoint at line number 14 and run the code. Okay. Let's look at the value of A and B. Print /xa. Okay, which is 2 power 20. You can see in both ways. This is first byte, second byte, and this is the third byte, right? And you get a 1 at, this is 16, right? This is 20, and this is 21st position. So if you count here, you will see the 21st position, I have the bit turned on, same as 2 port 20. And we do the same for B. We can print it in hex, which is 2 power 11, because this is the first byte, 8 bits gone, and 8 means 1 0 0 0, right? 0. That's the reason you get 8, and which is nothing but 2 power 11. Okay, so we got A and B ready, and let's look at the code again. We need to multiply. We already multiplied it right here. So let's look at C. We should see 2 power 31. Okay, let's look at C, or maybe in binary. Yeah, this is 2 power 31. This is first byte, second byte, third byte. 24 is gone, 28 is gone, and this is 32. So 32 position turned on means 2 power 31. Okay. All right. So you got 2 power 31 here. So I can explain one more time. 1, 2, 3, 24 bits gone, 28 bits gone, right? And then 8 means 1 0 0 0, 1 0 0 0 8, right? So 32nd bit is turned on. Okay, starting from bit number 1 as the position from the rightmost. Okay, which is essentially 2 power 31. Okay, so we got 2 power 31. And what about D? D should also be 2 power 31. Yeah, there's no difference between C and D. Therefore, the assertion will be successful when we return. Let's continue the program execution for the next input. And now we should check the new A and B. Okay, this A is 2 power 20, which is what you're seeing. 2 power 20. This is 16 bits gone, right? And this is 420 bit, and this is 21st bit, which is nothing but 2 power 20. Okay, what about B? This is 8, 12, and 13th position. Okay, which means 2 power 12. So 2 power 12 multiplied by 2 power 20 should give you 2 power 32. So let's print C, right? Print C. Yeah, you can see it's 2 power 32 because this is first byte, second byte, third byte, fourth byte. Okay, all the 32 bits are gone. And this is the 33rd bit position turned on. When 33rd bit position is turned on, it means 2 power 32. Okay. You have to reduce 1. All right. And look at the value in the D, which is 0, which is because 2 power 32 mod 2 power 32 is 0. So remember the code again.